So the first of the group presentations of differential equations, I would like to introduce my group member. So me, I am Wei Song, ID 22014, and we is my metric number. So below, they are my group member. So they are Chu Kunshun's, and his metric member is ID 220,133. Golden Sings ID 220,125. Lo Yawei ID 220,143. Li Jiefei ID 220,132. And also GUI 8220,158.
So at the first, we go on to the introduction part, and we will know that what is differential equation. Differential equation is a fundamental mathematical tools used to describe and model change the variation in various fields, and the ordinary differential equation and the partially differential equation. And the differential equation can be identified based on their order, linearity, and the homogeneity. And those methods including separation of variables, integrating factors, substitution, series solutions, and numerical methods for case where analytical solution is not available. Okay, now we go on to the physical model of suspension system. The suspension system is a little more than a collection of shock absorber and spring that attach the wheel to the car body. This is a somewhat oversimplified interpretation of the suspension system, though a car suspension system ensures that the wheel will stay in touch with the ground and reduce the vehicle roll while offering a comfortable ride across uneven terrain. And there got three main components make up the suspension system. And the first one is a spring that change kinetic energies into potential energy. And the second is framework that support the weight of vehicle and establish the suspension geometry. And the third one is mechanical device called a shock absorber that dissipate kinetic energy. So there are eight type of car suspension. So the first one is multi-link suspension, and the second one is rigid axle suspension, and the third one is Marshall-Hampson suspension, and the fourth is double wishbone suspension, and the five is independent suspension. Six is rigid suspension with lift spring. Seven is trailing arm suspension, and the eighth one, and also the last one is air suspension. So the advantages of a suspension system are improve the handling and ride comfort, and the second is increase the stability of car, and the third is improve the performance of the car while going through on the road. Then we go to the advantages of a suspension system. So the first is the financial cost because the suspension system will require a high cost to produce. And the second is technical complexity. And the third is also the last one, which is limited customization option. That's all from me. Thank you.
Now we come to the part of mathematical formula part. So first at the left picture, we can see that both have a M, which is a mass of vehicle. Below it, at the left side, have a spring, which have a K is spring constant of a vehicle. And the right side of this vehicle part is the shock absorber, which have a C, is the doubling coefficient. And for the reaction part, we got two is Y and V. Y is the vertical displacement of the spring mass, and the V is the velocity of the car in Y direction. So next we come to the right part, where we put all the force together. So for the force part, we got two force. First one is the spring force, which is Fs, and another we got a damping force is Fd, which is equal to Cv and equal to Cy. For the Fs, spring force is equal to Ky. So we put all the force together, we become, since F equal to Ma will become negative Fs, negative Fa, since we let above is positive, and we rearrange all the program will become My dot plus Cy plus Ky equal to 0.
So this is the sample calculation part for our group project of differential equations. So first is the equations of m d2y dt squared plus c dy dt plus ky is equal to 0. This equation is taken from the equation of motions. And so we let y is equal to e power rt, and dy dt is equal to the r times e power rt, and d2y dt square is equal to the r square times e power of rt. So we substitute the equation into the first equation that relate to the mode equation of motion, so we can obtain that mr squared by cr per k is equal to 0. So by using the quadratic equations, we can get three cases. The first is the equations where there is two real root, and the general solutions is set y is equal to c1 power times e power rt plus c2 e power r2t. And if the r gate is no real root or and is two imaginary root, the general solutions for this one is y is equal to e power of at and times c1 cos bt plus c2 cos bt. So there's another case that when solving these auxiliary equations, that is the two root get from the quadratic equation is the same, which means there is only one real root. So the equations, the general solutions for the equation will become y is equal to e power rt times c1 plus c2t. So let's explain the right side of the slide. A we we first get the initial conditions of the suspension system. So is the mass of car is 1,500 kilogram, and the speed constant or spring constant for car is 1,500 newton per meter, and the damping constant for car is 2,000 newton second per meter. And initially the car is at a height of 6 meters before it dropped to land. And initially the car is stationary, which means it has zero velocity before it drops by the pull of gravity of Earth. So to get the particular solutions for the suspension system, we start the initial conditions to the general solution that we get in the previous part. So we can get that R is equal to negative 2 per 3 plus minus sub 5 divided by 3i, which is an imaginary rule, a two imaginary rule. Because has no real root, the general solutions for this suspension system is y in the term of t is equal to the e power ft times c1 cos bt plus c2 sin bt. And then after we start the initial conditions, we can get that the yt is equal to negative 2 per 3 c1 power c1 times e power of 2 per 3t cos sub 5 over 3t and minus sub 5 over 3 c1 times e power of negative 2 per 3t and sine sub 5 per 3t and minus 2 per 3 c2 e power of 2 per 3t sine sub 5 per 3t plus sub 5 per 3 c2 e power of negative 2 per 3t cos sub 5 per 3t. And this is shown in this part in the right side of the slide. So, and also we apply the initial condition that stated that the car is initially at a height of 6 meters before it lands and zero velocity before it drops by the pull of gravity of Earth. Actually, we can get that the general solutions or the particular solutions for this suspension system is y in terms of t is equal to 6 per 5 e power of 2 per negative 2 per 3t times cos 5 cos sub 5 per 3t plus 2 sub 5 sine sub 5 per 3t, which is shown in the right side of the slide. So this is the end of the particular solutions for the suspension system. So by using the MATLAB, which is a programming and numeric computer platform, the graph of this suspension system behavior is plotted and it is shown in the right side of the slide. So it shows that it has a damping behavior. So this is the graph of displacement y against t, which means the displacement y is in vertical directions, up and down, up or down. So from this one, it shows that the car will undergo damping oscillations. Uh, it will have at least two oscillations for this condition. It means the car will be bouncing up and down two times when it dropped from its height of 6 meters and initially its vertical velocity is zero. Or you can say that it dropped from by the pull of gravitational of Earth.
discussion. A is a homogeneous linear ODE in the form of Px y prime prime x plus qx y prime x plus rx yx equals to gx, where the gx is 0. Since b squared minus 4ac smaller than 0, it has complex roots. So we use the general formula of y equals to exponential ax bracket c1 cos beta x plus c2 sin beta x to find its displacement. A graph of a suspension system can represent various aspects such as displacement over time, and the axis is x-axis, time, and y-axis is displacement. The graph of suspension system behavior is a critically damped system. A graph of a critically damped system typically shows the system returning to equilibrium without any oscillations. The displacement decreases rapidly from the initial displacement and then gradually levels off to 0. In the case, if the initial displacement is 6 meters and the car oscillates 2 times in 10 seconds, the curve starts at 6 meters on the y-axis, representing displacement at the time 0 second on the x-axis. The graph then shows a rapid decrease in displacement at 4 seconds, leveling off to 0 displacement over the 10-second period.
The advantage of the suspension system is quick response to disturbance. Critical damping makes sure that when there are disturbance like bumps or abnormalities in the road, the suspension system reacts quickly. When there is no oscillation or overshooting, the suspension quickly regains its equilibrium position. Second is reduced vibration and discomfort. Critical damping reduces oscillations in the suspension system, which lessens vibration that are left by the occupants of the vehicle. This makes the rider more present and smooth, especially on bumpy or uneven terrain. The next is improved road holding and traction. Improved tire contact with the road surface is maintained with the aid of critical damping. This contributes to increased vehicle stability and control by increasing traction during braking, acceleration, and cornering. Then, optimal energy dissipation. During motion, critical damping enables the best possible energy dissipation. While inadequate damping can cause bouncing or excessive vibration, excessive damping can cause energy loss. But striking a balanced critical damping ensures efficient energy dissipation. Next, stability during maneuver. Through its capacity to stop excessive body roll, essential damping acts in maintaining stability while on automobile mats, bends, or change lanes. This makes for more secure driving conditions and predictable handling. Then consistent performance across various conditions. From straight roadways to uneven terrain, critical damping offers a balanced performance in all driving situations. This flexibility guarantees that the suspension system manages various situation efficiency without sacrificing rider comfort or vehicle stability. Next, extend lifespan of suspension components. Reducing and the road strain out suspension component is achieved by operating near critical damping. This may lessen the need for frequent replacement by extending the lifespan of shocks and other suspension system components. The last is enhanced driver confidence. A suspension system test is close to reaching critical damping and is well then hits the driver confidence. Consistent and steady vehicle behavior enhance during enjoyment and boost trust in the vehicle's handling qualities.
So at the last, we go to the conclusion part. The superposition principle is widely used to solve the variety of a second ODE in real-life problems. So changing the equation into characteristic equation to find various solutions of an equation, we will know that the useful in the various scientific fields such as mechanical vibration, electric circuits, harmonic motion, structural engineering, control system, heat transfer, damp and force oscillation, and much more. And that's all from our groups. Thank you.